Good afternoon, everybody. Chair, just checking that you are there. Happy for us to kick off if you are ready.
Okay, I'm good. We can commence. Thank you. All right. Good afternoon, all. The slide vanished again. Okay, there we go. Uh, Thank you for joining the webinar as per the invite. I think today is fairly exciting and is the culmination of a project that has come many, many years in the making, and we can finally put a lid on it. Note that some of the members that were active before, like Kumbula, are actually on call. So Kumbula, this is actually a big day in terms of getting this through. But maybe just a comment in terms of, or a few comments in terms of who Coltech is. As you know, in the past 18 months, we rebranded Coltech for a much newer, vibrant type effect with a lot more social media presence than what was historically seen from Coltech in the starting years. Um, Essentially, Qualtech aims to drive collaborative coal research. All right, it's a voluntary non-profit organization addressing the research needs of the South African coal industry. As a footnote, it is also the longest running research facility in South Africa with respect to coal. Um, and we develop technology to ensure industry remains competitive, sustainable, and safe. And I think that lies primarily on the doorstep of our board, which is constituted out of industry players. And everything we study aims to actually address real-time issues that mines have in a short space of time in a sustainable manner and to a high quality. Um, by becoming a member, we've had a lot of associate members join Coltech, and I think what we offer them is this access to cutting edge research. Our research that we do isn't something that ends up in file 13 or in the bottom drawer. It is something that we can actually utilize and execute. Um, our associate members and even partners uh, can collaborate widely with the industry through the various theacoms. And they can also influence future technology. We know how the mines are. Not everybody's getting out all the time, and it's a rapidly evolving technological space. And a lot of them actually come to the table with many of the potential solutions for our issues going forward. And then through a number of events that are hosted and where the forum of Coltech is represented, there's the opportunity for strategic networking. I'm going to throw it in here. We have our colloquium on the 28th of May next year, and it would be great to see as many of the participants on the line over today actually join that. It is free to actually apply and join, and you can contact Rian. Is a mechanical engineer, well experienced with 25 years experience in the field of structural mechanics and performance testing of products, both at component and system level. Um, Rian holds a bachelor's and honors degree in mechanical engineering and a master's degree in engineering management. And they were all obtained from University of Pretoria. And he's also a registered professional with the Engineering Council of South Africa. I think importantly, relevant to this project, for the past 6 years, Rihanna has been responsible for the mine testing and training impact areas of the CSR, which includes the Cottesloe Mining Laboratory and the Klopperspoort Mine Fire and Explosion Testing and Training Facility. Rian was perfect to actually undertake the project because it's right in his backyard and he spent a lot of time, and I think we've arrived at a really worthwhile, comprehensive research study that was actually peer reviewed by both industry professionals and academics alike, as this is the first time that we can actually compare our testing methodologies to anybody else in the world. Without any further ado, I'm going to hand over to Rian Bear. Thank you.
Thank you, Chair. I'm going to put the slide on, and I would just like to ask confirmation if it is showing.
Yes, it is, Ria.
Good. Good afternoon, everyone. And Chair, thank you for the introduction. Yes, we at the CSIR and as part of the Kloppersbos team are equally excited about this project coming to a conclusion, and also excited to share the outcome, the learnings from the project with the audience today. Our journey today will start with giving the context for the work that was done. We will look at why we needed to revisit and upgrade the coal dust explosibility test method. We will also look then at a comparison that was done between the two laboratory apparatuses that Gavin mentioned, the 40-liter and the 20-liter equipment. We then ask how the real-world atmospheric conditions that one finds in the mine may affect the explosibility of the coal dust. And then finally, we ask, how can we take this effect or effects that it may have into account? I'm sure our audience today will no doubt be familiar with the catastrophic risk of coal dust explosions in underground mines.
Alright,
It therefore stands to reason.
you are listening to yourself. She's listening to herself. Give me the
Chair, is there a problem with the audio?
We've muted the individual. You may carry on.
Okay. It therefore stands to reason that an accurate and reliable testing methodology for coal dust explosibility is not just a compliance issue, but it's also essential, as it could be the last line of defense for the safety of people working in the mine. I'll just try and draw a line from the lab test result to how that is used in decision making and implementation of a dust explosion mitigation in the mine workings. So our lab test result produces a value called the explosibility index. Traditionally, this is a KEX value determined in the 40-liter explosion vessel in the lab. And this explosibility index is then used to classify the explosion propagation risk, which we will show later. There are 3 categories. Based on this classification, explosion risk mitigation strategies are then designed and implemented. For example, mitigations may include the elimination of ignition sources and dilution of the methane that may be in the mine through sufficient ventilation. However, if those mitigations fail to prevent an ignition source, for example, a methane ignition in the mine, the last line of defense would be the application of stone dust to inertize the coal dust and ensure that it will not propagate an explosion. Now, as we've said, the explosibility testing of coal dust at the Kloppersbos facility has been done using our 40-liter explosion apparatus, and this has been the case for, for several decades. That testing approach has served us well by and large, but unfortunately, it must be said that we have lacked the ability to have independent calibration verification of that equipment done for some years. And that has obviously raised the question about the validity of the test results over such an extended period. We also have an alternative apparatus, as was mentioned, which is the 20-liter explosion sphere, or the CIWEX sphere, as it's also known. And this 20-liter apparatus is an international standard in dust explosibility testing, not just coal dust. It's used for testing of other types of combustible dust in laboratories across the world. However, we have never before determined any correlation between our historical data that informs these dust explosion risk classifications or categories that I mentioned, and results from the 40-liter vessel to the 20-liter vessel. And lastly, whichever one of these equipment we are using, when we test in the lab, it is done under lab atmospheric conditions in terms of temperature, humidity, and there's no methane involved in the test. And we know that these the temperature and humidity can be different in the mine. It probably will be different in the mine compared to the lab. And there is the possibility of there being some concentration of methane present in the mine. And if the methane dilution does not happen as it's intended to be, the percentage of methane can be such that it has a significant influence on the coal dust explosibility, as we will show in the results from this work that we did. Now, from the aforementioned problem statements, we were able to then define or state the following two core research questions. Number one, can the 20-liter apparatus reliably replace the 40-liter for routine testing? And number two, how do the atmospheric conditions in the mine affect coal dust explosibility? And I think a addition to that would be, if we know how it affects it, how do we account for that? Let me just take a moment to introduce these two apparatuses that we have in the lab for dust explosibility testing. On the left side, in the left side photograph, you can see the 40-liter apparatus, which, as we mentioned, was used in the original research into coal dust explosion propagation. It has been our local standard in South Africa for decades, but unfortunately, it lacks that independent calibration verification. Another issue that we have with the 40-liter apparatus is that we lack technical support from an OEM or from an independent source, whereas by contrast, the 20-liter apparatus on the right-hand side is a widely recognized standard equipment for dust explosibility testing. The system is regularly calibrated via an international round-robin testing scheme administered by the equipment manufacturer, and we have comprehensive technical support available from the equipment manufacturer. And with that contrast, I think makes it clear why we felt that it was desirable to see if we could migrate the coal dust explosibility testing from the traditional 40-liter apparatus to the 20-liter. Our experimental methodology consisted of two phases. In phase one, we carried out step-by-step testing in both explosion vessels to determine if we could establish a correlation, and if so, what that relationship is.
Horizon fast.
Then, having established this relationship between the two apparatuses, our phase two testing involved a series of tests under conditions where one atmospheric factor was varied while keeping the others constant. Then from the test results, a set of factors were derived for adjusting the laboratory test results to real-world mine conditions. The results of the phase one testing showed a meaningful correlation between the explosibility KEX value obtained from the 40-liter vessel and the corresponding Kmax value obtained from the 20-liter vessel. Now, what is the difference between KEX and Kmax? I won't dive into the detail, but it is basically a number that represents the severity of the explosion. It is closely related to the rate of pressure rise inside the vessel. And from that characteristic, the research that was done in the past indicated that one could use such a characteristic value to classify a specific coal dust sample in terms of whether or not it was going to propagate an explosion or not. And we'll get to those categories in a few minutes. So we established the mean ratio between the KEX value and the Kmax value as 0.97, and the grouping or the spread of the data was such that the standard deviation on that value of 0.97 was only 0.08, or expressed as a percentage of the mean, only 8.3% of the mean. Now, this result indicated that the 20-liter apparatus may be used for routine coal dust explosibility testing. We could continue with the 20-liter vessel to replace the 40 because there was such a neat correlation between the two. We can now express, with that relationship established, we can now express the well-established and well-known explosibility classification of coal dust in terms of results obtained using the 20-liter apparatus. Now, in the slide, you will see that we have the three categories or classifications: non-explosive, transition, and propagating. The first column of values are the KEX values that we are used to when we are testing using the 40-liter apparatus. The second column of values are the corresponding Kmax values obtained in the 20-liter apparatus. Now, if I can sum it up as follows: in the range of KEX values up to 70 or Kmax values up to 68, the coal dust is considered non-explosive and will not propagate an explosion. Note that this is now a statement for the result obtained under laboratory conditions, and we'll see how in a later example how that can change. In the middle range, or the transition range, for Kmax values between 68 and 93, this is considered a gray area or inconclusive. This coal dust could still propagate an explosion, and the recommendation is to do a large-scale test to determine if it will propagate. But due to the amount of work and the cost involved in large-scale testing, this is often not done. A practical alternative could be to simply treat that dust as a dust that is likely to propagate an explosion. In other words, treat it as category number 3, where we see that for Kmax values exceeding 93, this indicates a high risk, and it is likely that the coal dust will propagate an explosion if it is not innertized with sufficient stone dust. And now we get to the atmospheric conditions. Mines are not like laboratories, and we need to address the second of those two research questions. How do real-world atmospheric conditions influence the explosibility of the coal dust? Does it change the explosion risk classification? In other words, does it lead to a decision to introduce inertization with stone dust? And if it can lead to that, how do we account for this change? How do we calculate what it must be? I'm now going to just briefly mention or show the results we obtained for each of the three factors, and then we will combine them into a way to adjust the lab result for real-world conditions. Firstly, temperature. Higher temperatures increase the probability of coal dust to propagate an explosion. We found that 1 degree Celsius increase in temperature increases the Kmax value by 0.4. I thought maybe thinking about a 1 degree change is not such a practical thing, because if we go from laboratory to mine, I think it's possible that the temperature difference could be 10 degrees. So if we take that into account, then 10 degrees change in temperature is a 4 bar meter per second increase in Kmax. Next, we can look at humidity. And we found that a 1% relative humidity increase will reduce the Kmax value by 0.3. Once again, if we take a reasonable difference, a difference of, let's say, 10% relative humidity change, that means 10% more humidity. will decrease our Kmax value by 3. And here's the important one, I think the one that we all need to take very good note of. A 1% increase in methane concentration in the air in the mine will increase the Kmax value by a whopping 22 bar meter per second. And why is this important? If we consider this together with the methane and also together with the temperature and the humidity, we can expect that it could possibly change the classification from not propagating into the gray zone, or from the gray or uncertain zone into the danger, the high risk zone, where it will propagate. And we'll show that in the example later. I'm not going to spend a lot of time on this slide diving into the detail of the data, not during this session. The research project report is available online on the Caltech website, and the detail is set out in the report. These graphs do provide us with a visual representation of the data that we collected at discrete atmospheric conditions, and we can see the impact of each factor on the explosibility being represented by the coefficient of the straight line that was fitted through the data. So once again, we note the impact of methane being dominant, where the coefficient in the methane graph is 21.977, or if we round it, 22, whereas the coefficient in the other two curve fit graphs are both less than 0.5. So less than 0.5 compared to 22, relationship. It is clear that we need to adjust the laboratory test results for real world conditions in the mine. And the formula that we show on the slide here makes this adjustment easy to do. So our Kmax value in the mine, or for conditions in the mine, is simply our Kmax value obtained in the lab plus the adjustment for temperature minus that adjustment for relative humidity, or RH, in the formula, plus the adjustment for methane, the CH4 percentage one that you see in red. Let's look at a practical example. The lab result in this example gives us a Kmax value of 69, just a shade under the limit for the gray area. So one might look at this example and say, okay, wonderful, our coal dust will not propagate an explosion. But then we take into consideration that our temperature in the mine is 28 degrees C, whereas the lab was at 6 degrees less. And our humidity is at 60% relative humidity, which is 15% more than in the lab. And we make allowance for 0.5% methane in the mine's air, whereas in the lab, we didn't have any methane in the explosion vessel during the test. We then calculate those adjustment factors, as we see there, and we arrive at an adjusted explosibility index value of almost 78, which places this result solidly in the gray area, where it is not possible to say that the dust in that mine under these conditions will not propagate. It is then up to the user of this information to decide how they would like to treat that risk, but clearly it is not the same risk as in the case where we simply consider the raw lab result without taking the mine conditions into account. So we believe the critical insight that we find from this work was that our standard laboratory test may underestimate the true explosion risk in active mine sections. A dust that could be safe can become explosive when combined with even low levels of methane and high temperatures. So in conclusion, we validated our use of the 20-liter explosion apparatus in the laboratory to replace the 40-liter apparatus. Secondly, we find that methane dominates the equation. Even a small amount of methane drastically increases the explosion propagation risk, and it far outweighs the other two factors of temperature and humidity. And then finally, the context of our mine operation atmosphere is critical. And therefore, we have to adjust our lab results to take real world conditions into account. We have a few recommendations following the conclusion of this project. The first is to formally adopt the 20-liter explosion apparatus as the primary equipment for routine testing of explosibility of coal dust. Secondly, at the use of these adjustment factors that I've shown should be mandated and to be used to derive the adjustment formula for the to translate the results of the lab to the mine condition. And then lastly, to conduct some further testing at low methane concentrations to further validate the hybrid mixture risk threshold that we found. Simply because this is the dominant factor, we recommend that some further testing should be done around that point to have a better insight into whether that relationship is nice and linear, or whether there's maybe some non-linearity that we also need to take into account, or any other factors that we have not found yet. So the remaining gaps, if I can just summarize. First of all, real-time monitoring in the mine can significantly add to the knowledge of the risk. Sensors that can continuously track the hybrid mixture, the air methane mixture, can inform in real time the change in explosibility risk in active mining sections. Secondly, the standardization to establish industry-wide protocols for applying this adjustment factor, and to have uniformity of application of those adjustment factors throughout the industry. And then lastly, validating the correlation that we found across a wider range of coal ranks or coal samples. We saw in one of the slides that our coal explosibility test results didn't represent the very low range of explosibility index values, and it didn't extend into the very high range. And so we recommend that some further testing be done to explore those ranges. Then in conclusion, I think what we found from this work and how it translates into application in the mine, that we are not just generating numbers when we test in the laboratory. By doing this project and refining our test method, we see that the numbers that we generate, that we produce in our test report, can and should be used as part of the mine's effort to engineer the safety and the survival for every person that goes to work underground. Ladies and gentlemen, that concludes the presentation, and I look forward to some engagement around questions or discussions on the topic. Thank you very much.